This is a great honor. Thank you, Dr. Maldonado and the university and everybody to do this. It's probably the most diverse symposium I've ever talked to in the last 25 years, but it was inevitable. It started with pain, went to coma, it went to death. And now I'm supposed to talk about brain rehab. It's too late, no. It's over. No, I'm just kidding. So actually, there are amazing connections we can make, and some of the connections, auditory, make a movement audible to help proprioception. The auditory pathway is intact, even in disorders of consciousness to many extents. So there's lots of things we can talk about. Anyway, so the other nice thing is that I'm coming back to Canada with a tan, and that may create some problems at the border, because the border police is very white, because it's winter right now, so they don't like people come in with a tan. So anyway, so I'm a professor at the University of Toronto, and we have a big institute for rehabilitation, neuromusic rehabilitation, and then we also have a graduate program for music and health science students. And if you're interested, you can contact us. And one of the interesting things is that we come to talk here in a few seconds, is that there is an Academy of Neurologic Music Therapy that has been built on a lot of my research, but also other groups' research. And this is an international training endeavor, and it could, we have very interesting discussions, maybe to bring this for South America and the world right here into Quito. So, a little bit of context. I do clinical music neuroscience 70% of the time. I do some basic music neuroscience perception. So what is clinical music neuroscience? We investigate supramodal translations of brain processes in music perception, cognition, and creation, and looking for translations to improve brain health and neurodevelopment. I was a professional violinist for many years, and when I didn't want to do that for the rest of my life, I became interested in the science of music. I was always interested in that. But the last thing I wanted to do is study how musicians perform and put musicians in a brain scanner. That would be, for me, the most boring thing, because I already did this, and I don't want to know how my brain did that. But I wanted to know if some of the principles and mechanisms that made me sort of a top-level performer could be translated into mechanisms that could help non-musicians in neurologic disorders to recover their function. So supramodal means we are not looking at trying to use music to help people understand music better, rather than we are trying to translate musical experiences and techniques to non-musical experiences and rehabilitation purposes. So to make this a little step clearer, for instance, in music perception, one of the first questions we asked, there was actually, we'll see some of the videos, can musical beat perception help people, let's say with stroke or Parkinson's, walk better, not dance better, walk better functionally? Or in studying the mechanisms of music cognition in the structure of music, can that help to shape auditory general attention or memory, not musical memory, non-musical memory? And you'll see some applications of that. And creation, can mechanisms in music, performing music, for instance singing, help people to create speech abilities again? For instance, aphasia, the left hemisphere is damaged, and singing words transfers that language functions to the right hemisphere, which is undamaged. So there's access to an alternative network that music provides us. Or as a musician, or in music, we make movement audible So I stay and I play, and all my movements become audible into sound. So can we map people who have issues with their, let's say, arm function, map their movements, functional movements, onto musical instruments? They get augmented feedback, they get the rhythmic structure, and do they improve? So that's behind this major sentence, and I wanted to spend a little bit of time on that. So what's neurological music therapy? It is the clinical branch that developed off the research. So I'm not a neurologic music therapist technically, but I try to provide data for therapists. So it's an evidence professional field, and NMT applies in the interventions to 3 domains. One is sensorimotor, speech language, and cognitive rehabilitation, and I try to show bits and pieces of clinical applications and some of the science underneath this morning or afternoon. There are 20 techniques, and the rhythmic auditory stimulation technique for gait, for stroke, is already in the National Critical Care Guidelines for Stroke in Canada and the US. And we saw some nice applications, spontaneous application in the clinic, Dr. Maldonado's clinic yesterday, with some 2 very severe traumatic brain injury patients. Good, that's the NMT Academy. There's this famous code that we need nowadays to eat, buy milk, drive cars, and that kind of stuff. So if you want to take that down, you can get access or use the website. And this is the distribution of trained and certified neurologic music therapists across the world. And you see there is some presence in Brazil and Argentina, not much in Ecuador, but I think we can change that and make that actually not just a center for Ecuador, but also for a large part of the world. So, I'm going to show you only 2 slides out of critical mechanisms, brain mechanisms, connectivity issues between how the auditory system shapes the brain. The auditory system processes and measures time. That's the basis. Okay? The auditory system processes sound waves, vibrations, molecule, air molecule vibrations. So the auditory system is specialized in rapid time communication and in enormously precise amounts of quickness and precision. So there is auditory connections to the rest of the brain, basically from the cortex to the spinal cord. So I'm just going to show you 2 to get you an idea, and appetizers. One is, this is the acute fasciculus. It's an awful name, but it's very important, so I have to use that name a lot in my daily life. And this is not schematic, this is microscopic imaging, and this is the auditory cortex right here. And these are pathway projections into the prefrontal area, executive, speech encoding, but the orange stain, and we made a special purpose out of that, is direct connections to the premotor and primary motor cortex. So auditory information is directly on the cortical level, synaptically connected to the motor system. This is an interesting slide because it shows you how auditory rhythmic information can shape motor output. Auditory rhythmic input shapes motor output on the EEG level, the brainwave level, and it also is then reflected in improved motor performance. So these people were tapping, these were healthy people, they were tapping to a set of rhythms, self-paced, and you can see there is somewhat of a certain relatively fuzzy periodicity in the motor signal of the EEG. Then we had them listen to the same tempo to an auditory beat, and there are very nice, precisely reflected auditory field potentials, and then they're tapped to the beat. And now you can see how the auditory information, the auditory signal, reshaped the motor signal from here, a relatively fuzzy signal that's not very precise in time, to a very precisely defined auditory motor potential in the EEG. And that's also then reflected in them tapping in a much more stable pattern. And these are some of the mechanisms that are underneath the clinical translations. So let's look at rhythmic auditory stimulation. That's a big technique that has been proven to be very successful in the last 20 years, especially for Parkinson's and stroke. So I'll show you a video first, and then we can talk a little bit about that. You see a cerebellar ataxic patient first, and then you see a stroke patient from one of the major studies we've done in the late 90s and 2000s. So this is a cerebellar patient. You see a classic ataxic gait pattern, wide stance, sequencing very poor, lots of balance issues.
You know what, it was great after that. Right there. Thank you so much for your work. No cheating on the bar. Oh, really? Okay. Okay. Stop. Really? Yeah. Just while it was happening.
Oops, go back there.
You know what, it was great after that. Right there. Thank you so much for your work. No cheating on the bar. Oh, really?
So now we're adding
Okay. Stop.
a simple metronome beat at the same frequency as a step frequency was. And so he immediately changes. And that took a while for us to understand why that happens. So we had to do a lot of modeling, thinking perceptual motor, initially kinematic models, math models. Now we have done a lot of neural work on that. But the funny thing is, and as a musician, we know that intuitively, but we needed to translate that. You add a time constraint to your movement. You know when you start your movement, and you know where you have to end it, when you have to end it. Everything in your control of the movement changes. And we've done that with athletes, et cetera, et cetera. So the simple addition of an anticipatory time signal, time constraint, changes how the brain calculates, controls, and implements the movement. Let's take a look at the stroke patient. So that patient is 4 weeks post-stroke and has an MCA distribution injury. That's an old lab setup. We look a little slicker now. But you can see basically that there's not much in terms of sequencing. There's so many kinematic things in the trunk rotation and the anterior-posterior direction. There's so many things wrong. So that's the immediate effect of the addition of auditory rhythm, now embedded into rhythmically enhanced music. And if you look carefully, especially when you see him from the side, you maybe get an idea what changes in his control of his legs, especially the paretic leg. So keep watching carefully. Look at that left leg. And that is 6 weeks later. So these tests are done without music, of course. So I think you may have been able to see that because he had an anticipatory time constraint, he started moving his parietal leg earlier. So his motor neurons were not healed, the network is still damaged. But the control that he imposes on that system changes how he walks. And then the walk 6 weeks later, so that would be 10 weeks post-stroke, that is a very remarkable, beautiful walk, and we did some studies on that, compared it to other physiotherapy methods, and we showed in all the key parameters for gait, velocity, stride length, cadence, symmetry, et cetera, we showed significant improvements. So RES is a standard in many parts of the world, and we have seen some spontaneous great things yesterday. Okay, Parkinson was this other one, big movement disorders we studied. Very different pathology. And here are some pictures. So you see all the Parkinson mobility issues beautifully in that parkour that they're set up on purpose, so it makes it difficult for him as to navigate. So we did some brain imaging, not walking, but hand movements, rhythmic, and some of the interesting findings was that we have a lot more cerebellar involvement that sort of seems to assist the basal ganglia because the basal ganglia is dysfunctional. And we only saw that cerebellar involvement when we did it with the Parkinson patient. The healthy people didn't have any extra cerebellar involvement when they had the rhythmic cue. And then, interesting, talking about networks, the motor cortex here becomes sort of a hub for down regulation. So in other words, the addition of a simple metronome created a assist network that changed the whole motor control, underlying motor control system. Here's a very dramatic example, different type of Parkinson. Right immediately after. So these are clinical pictures from all over the world, so this is not all in our research lab. Most of that is actually not done in our research lab anymore, so it's not the air in Colorado and Toronto that makes that happen. Okay, so let's skip that. We did a big study on reducing falls in Parkinson, which was very successful, was published in 2018. And we are doing now at the university, it's one of the few places in the world where you can actually do neurotransmitter imaging. It's very different. You do biochemical imaging and PET scanners. It's very different than what we've seen so far in terms of more topographical imaging. So the interesting thing is that we actually saw in the basal ganglia a reduction when they did rhythmically, musically paced movement. We saw a reduction in dopamine uptake, which initially defeated our hypothesis because we thought the music will enhance the dopamine. There's not enough in the basal ganglia. Maybe that's why why Parkinson's patients walk better. So like a residual stimulation. No, it's actually the opposite. So apparently, and that's what we are trying to reason, is the addition of the music rhythmic cue to help them to organize their walking reduces the reliance on a faulty neurotransmitter system. And so that's how we reformed our hypothesis. So in other words, the sensory stimulus reduces the need to rely on a system that is not, the biochemical system that is not present functionally. So that was a very interesting finding we published 3 years ago. And this is what we're doing right now. There's another teaching hospital. The University of Toronto has 10 teaching hospitals, and we're collaborating with 7 out of them. And there's one hospital, Toronto Western. They do DBS surgery. They do it staged. So they do it open the skull, they put the implant in, and then they keep the wires out, and they do all kinds of testing. And then 3 days later, they close everything off. So we have, for a 3-day window, for a patient who agrees to record our rhythmic synchronization paradigm. And we did this, and we just published, we haven't published that yet outside of an abstract at the Society for Neuroscience last November. So this is very interesting. So this is intracranial recordings. So this is as far as I can go, not being a molecular scientist. And we are seeing when self-paced movement in the intracranial space, in the globus pallidus internus, we've seen basically a sort of tonic, semi-desynchronized potential. This becomes perfectly synchronized. The neural output becomes perfectly synchronized when we add a rhythmic beat to that. And behaviorally, the finger tapping becomes much more stable. So we have a pretty good idea, more and more idea, why this stuff works. And we are very happy with those data. And I want to move out of gait for a moment. I have maybe another 7, 8 minutes. Can this work for the rest of the body? Yes, it can. Outside of gait, no other part of movement is oscillatory based biologically. So we have to create cyclical movements to sort of simulate the idea of RES on gait. And so this is an example from neuropediatric work. These kids have various cerebral palsy, some have early strokes. And so the musical instruments are placed in space to force functional movement. So this is not a free jam session at all. Okay, and this is a group, elderly group. Some of these people have strokes. You get the idea. And we have done a major stroke study with this particular technique, which we call TIMP, Therapeutic Music Instrumental Playing. Jonathan was on the dissertation committee, and the data look actually extremely exciting because the Fugelmeyer tests and the standardized motor tests showed significant improvement with the addition of this musical rhythmic setup. The data I want to highlight a little bit are more deeper kinematic mechanism data. We put acceleration sensors on the limbs of the stroke patients. Acceleration sensors measure the change in speed. And this is where we saw tremendous improvements over those 9 therapy sessions in terms of peak power of acceleration, which means the patients were more and more able not to move faster, but to change intentionally the speed of their movement. And that, for us, was a great breakthrough, and we got it published, and so maybe other people thought so too. And also the acceleration width and the consistency of that ability to move faster, to accelerate, to decelerate, was clearly available. So this setup that I just showed, this clinical setup, which actually patients love, especially kids, has some very interesting embedded mechanisms. Quick look at speech and language. Let's go to this fellow. Let's do it in Japanese.
お名前教えてください。
So here's a classic Broca's aphasia. He knows what he wants to say, but he can't encode it because his Broca's area is not tangible, intact. So cannot say it. But he can sing spontaneously a song. And now she's trying to work with him with the same idea on functional words. And so konnichiwa, that's a Japanese word for hello. Probably most of you know that. So melodic intonation therapy is a very interesting application. It's a very long-term process. You have to train a lot, but people get better. And these are interesting data from my friend, colleague, Gottfried Schlauch in the US, who actually had a patient where he did melodic intonation therapy, and you can see the plasticity in the arcuate fasciculus connecting on the right hemisphere, connecting the auditory system, the perceptual system, to the right-sided Broca's homologue. So right here now you see more connectivity, active connectivity in here. So the MIT music-based speech interventions also induce brain plasticity. Here is a great picture, muscular dystrophy. I love that. You can see how the guy begins to breathe strong and rhythmically. Okay, so attention, let's skip all of that because we're coming to the last big thing we're doing right now is memory, wonderful, is we're looking at this. There's been a lot of reports, anecdotal reports mostly, that patients with Alzheimer's disease remember musical stuff much more than the rest. They're singing you songs that they've known for 30 years ago, and they don't remember what they ate 5 minutes ago. So we did a study where we created playlists for music that they recognized and identified for, this is my favorite music for the last 25, 30 years. And we had them listen to that in the brain scanner, fMRI study, and we alternated that in a scanner with music we had freshly composed in the same style, so you want to match the style, but they only heard that music 1 hour before the brain scanner for the first time. So we could contrast in the scanner a network of 30 years plus music, memory, and 1 hour. And these are the data. So we see in red the long-term music network, which is a widely distributed, deeply encoded network, cerebellum, basal ganglia, not affected by the disease. We have prefrontal areas, so we assumed that some of the triggers of this surviving network had something to do with autobiographical salience. And the 1 hour music memory network was basically, in blue, is basic auditory sensory-based network. So that probably disappeared within a very short time. Then we had people listen for 3 to 4 weeks daily to their familiar, autobiographically relevant music, and we found actually increased functional connectivity in 2 brain areas, inferior frontal gyrus and thalamus, and cingulate and prefrontal cortex. We found changes in the white matter density. We did a white matter microstructure analysis, and we also did a neuropsych workup before and after the Montreal cognitive assessment. And fascinatingly, we found actually in the memory subsection, we found statistically significant increase. And we were, especially my non-musical cognition colleagues, were quite stunned by that, because this group does not improve, and we are not claiming to cure Alzheimer's, but I think these data for the first time show what is the neural network that survives to a certain extent, or for a certain lifetime, and how can that provide cognitive boosts for these people. So, we have a lot of collaborators. Hopefully we'll add the university here and Dr. Maldonado's clinical system. And we have a lot of PhD students, almost too many. And we have postdocs and a couple MA students and research coordinators. And I ended with this because this is a very practical application. This is an NMT, Neurologic Music Therapy trained physician in Norway, working very practically with a patient with Parkinson's disease. Thank you.
Thank you, Dr. Thaut. That was fascinating. I think we have time for one question. Okay, 2.
Thank you, Dr. Thaut, for sharing your knowledge and work with us. My name is Maria Sol. I am a professor here at the university. And with some colleagues, currently we are working in a project using music for a spatial neglect rehabilitation. So we are trying to build an app where you can drift the sound from the side that is unattended to the side that needs the rehabilitation. So we now are using music, all equatorial music, because we think by the emotional side the patients will like it, but we were wondering, maybe in your experience, like a gender or subgender or frequency that suits better for rehabilitation?
Hemispatial neglect?
Yeah.
I will answer that with a video.
Okay.
Okay,
this is the hemispatial neglect patient. That's very clear to see. He finds the things, looks at the wrong side. And the training, musical neglect training as part of neurological music therapy follows these principles. Oops, sorry. You set up let's say tone bars is excellent, and you set up a musical system that the patient somehow knows how to complete, and you put the completion bars into more and more into the neglect side. So this looks right here. So this therapist uses it on an octave because we have a natural understanding of where an octave is because of the overtone sequence. So people know a D and an upper D or lower D is the same note. You don't have to be trained musically. After I don't know how many sessions, she's gotten a lot better. You can test it. There's a very simple test, the line crossing test, Albert line crossing test, circle test. And we actually published a paper on that in Frontiers in Neurology. And we created this technique 20 years ago, when we created all the interventions that was supposed to belong to Neurologic Music Therapy, we found one paper in support of that. We didn't want to use just build a technique just on one paper. But we said, that sounds so logical. So we tried, and people took it, and the therapists took it, and it worked extremely well. And now we have probably 10 or 12 papers that in various different configurations show that. So if you do this kind of research, you're on a fantastic track.
Thank you so much. So now we can have this support also for this kind of disorder, right? Thank you.
Oh, no, 2 thumbs up, sorry.
Hello, thanks for the presentation. So this question is not so related to therapy, but the motor system's relation with music. And so understanding that we tend to synchronize our motor abilities with the beat we're hearing. For example, when we're hearing and following a certain beat, for example, 100 beats per minute, and we are dancing or playing an instrument or walking, why is it so difficult to not follow the beat and try to break the pattern or to do polyrhythms in music? And what does this activity causes in the brain, like maybe improving neuroplasticity or an effect?
Yeah, so we, just to answer the last thing first, so we know that the addition of rhythmic auditory stimulation changes clinically, behaviorally the patients walking, but we also know that it induces brain plasticity. We know that, and I try to show some of that stuff. So why can we not escape? Or we can, but it's very hard to escape, because we are talking physically about this. What our first math models actually showed that we are talking about entrainment models. Okay, and entrainment means an oscillatory body that is very prevalent, strong, entrains a secondary body. So the auditory neurons, if you remember the arcuate fasciculus, the pathway, auditory neurons synapse with motor neurons. So auditory neurons listen to the beat, they fire, and the motor system fires along. Okay, and we call it a weakly coupled oscillator, because fortunately, if it would be a strongly, you could truly not escape, and I can turn a metronome on and make you walk into the wall. So it's a weakly coupled oscillator. That means it is primary, but you can obviously still escape from it. But the effect is very strong, and the idea that the auditory system has very close, strong connections to the motor system from brainstem, reticulospinal pathway, all the way to the cortex, that was anatomically known for a long time, but not functionally understood that well.